In this concept video, we're going to talk about the mechanism of the Michelson interferometer. The Michelson interferometer is a common configuration for optical interferometry and was invented by Albert Abraham Michelson. The principle of the Michelson interferometer was employed in many scientific experiments and became well known for its use by Albert Michelson and Edward Morley in the famous Michelson-Morley experiment 1887, as well as the well-known LIGO experiment, which made the first observation of gravitational waves.
Before we get to Michelson interferometer, we need to understand the concept of interference. Interference is a common effect in physics, which governs the world we're living, as well as Michelson interferometer. When we talk about interference, we'll talk about constructive interference and destructive interference. If we had two identical waves with same phase, which means they have the same amplitude for the same value of x, the sum of the two waves will essentially have its amplitude doubled at every point, and that's called constructive interference. While for destructive interference, the two waves would have a phase shift of pi, which means that they are essentially inversed, so at every point of x, the first wave will be countered by the second wave. So how could phase difference arise? It's all based on path difference. If the path difference between two rays are of n plus 1 lambda, they will be in phase and constructively interfere, while if the path difference is a half n plus 1 lambda, they will destructively interfere. Then how do we determine path difference? In general, it boils down to 2d cos theta, the geometrical difference in the root take, times n, the refractive index of the medium.
Now let's introduce you to the Michelson interferometer. This is a beam splitter which splits lights, monochromatic in this case, equally into two beams that are perpendicular to each other, forming the two arms of the interferometer. On path A, A beam is going into the glass one time, two times, comes out, get reflected on a movable mirror, goes back into the glass a third time before reaching the screen. On path B, the light beam will only transmit to the glass one time, then get reflected on a fixed mirror, then it will be reflected again on a beam splitter and reach the screens. Because they go through the glass different number of times, we have to balance them by putting a glass called compensation plate within B arm, so that the B light goes through it twice, making a total of 3 times equal to in path A. Now we can investigate the path difference between our A and B light beams. The path difference is actually just 2 times the length of B minus A, which we define as d, and the n terms, which only depends on the properties of the medium that the light goes through, is the same for the both rays. The theta term will arise if the move of a mirror is tilted, which is not happening in this case, hence the two beams are parallel to each other.
Now, knowing the path difference, we can check it against the value of lambda to see if it satisfies the conditions of constructive and destructive interference. If we want to be more precise, we can calculate the amplitude for any point on the screen by adding the wave equations of the two beams, which will give us an expression for amplitude of the combination of the two waves, which looks like this. There is a coefficient 2 in the equation because the path A and B are propagated twice by the beams, Rx. I is the imaginary number. And here we are motivating Euler's equation to give us a trigonometric function. Now, what we see on the screen is not the amplitude, but the intensity of light, which is calculated by taking the modulus of the amplitude and squaring it, yielding us this expression for the intensity on the screen. Now, we expand the argument of our cosine to give us an expression in terms of lambda, d, and theta from our previous expression for path difference. From this expression, we can infer the pattern that we're going to see in the screen, as the intensity only depends on d, which is constant for the same setup, and theta, which changes from a point in the center of the screen to a point separate from it. Hence, our fringes will be circular.
This phenomena has many useful applications in modern-day physics. For example, measuring the refractive index n of a medium, the thickness of a very thin material, and more amazingly, angstrom-sized vibrations in spacetime due to passage of gravitational waves. A famous example of this is at LIGO, where the warping of spacetime caused changes in the optical path of the light beams. This caused a change in the path difference and hence phase difference between the two waves, initially in antiphase, which resulted in a change in the intensity of the superimposing waves at the detector. As you can see, the applications of the Michelson interferometer have paved way for many modern physics concepts and will always have a place in any UCL physics student's heart.